Welcome to the GoldSim webinar. This is a webinar that will be on modeling discharges from ponds and reservoirs. And I welcome all of you. Thank you for joining. And I hope that this will be a useful presentation, especially for those of you doing water balance models and working with storage systems in which you are moving water around between or from ponds and reservoirs. The concepts that I'll be talking about for the most part are fairly fundamental to building these kinds of conceptual models, mostly with the one-day time steps is what we'll be looking at. And so these will be applicable to a model such as a mine water balance model or a water resources model with fairly large systems in which we are looking at the kind of bigger picture of overall operations and not so much at the more detailed hydraulics that you might see with models with very short time steps, though I will talk a little bit about that. In fact, the model that I'm showing right now has very small time steps, but this is just for demonstrations to start off with. So what I'll do is I'll start with this model just to give a demonstration of some of the things that GoldSim can do, and then I'll get into the modeling concepts. Okay, so this is a model that simulates an outlet works on a dam that has 5 gates. These are represented as, well, the equations being used are assuming this is a radial gate that shuts down onto a smooth like OG weir. And so what it does is over time, as the water level in the reservoir changes, as it's increasing, for example, then these gates will open in an order. There's a priority to these gates starting on the left. And as the water level rises, continues to rise, then the next gate to the right will then open, and the next one to the right will open, and so forth, in order to try to maintain a water level in the reservoir behind it. And there are times when the gates are open more than what the water level, or they become not submerged gates, so they can switch between submerged and not submerged. So the equations have to change from a weir equation to an orifice equation. So that's kind of what's going on behind the scenes here as we play this model. And I will be running this model in slow motion. So I've moved this slider over to slow motion, and now I'm hitting play here. And over here on the right is a chart of the flows through each of the gates. They're different colors. The dashed line is the water level, just for reference, but well, this orange dashed line. But these other colors represent the flows through each of these gates. And you can see that these are opening. These are just the thermometer controls in GoldSim, and I just have the colors set to yellow, or I mean blue and black. Realistically, there would be a third color, which would be, I guess, white, showing that there are times when this is shown as weir flow, that there would be a gap, a white little area, indicating that the gate is not submerged. So I know visually it looks like the gate's always submerged, but it's not. But anyway, so that ran through time. You saw the gates opening and closing. So what's going on behind the scenes here? If we go into the model, oops, clicked the wrong thing. If we go into the model here, then what we have is a pool element to represent the pool of water in the reservoir. And then we have the gate controls, which is where most of the calculations are going on. So over time, we're keeping track of the water level. And then we have all these gates. And for each gate, which is a cloned container, by the way, because they all have the same logic, right? So I've cloned the container so that any changes I make in here will be then cloned to the others. So the functionality is the same, but the difference is that they have a different priority on when they start opening and closing. So I have calculations for weir flow here, and we could look at more information about that. And then I have orifice controlled flow here. So anyway, that's the kind of thing. This is a lot more detailed than what I'll be getting into covering these concepts, but I just wanted to show you kind of, where some ways you can go with GoldSim and its functionality. So let's start now looking at some of the concepts I want to talk about. Okay, so the first one I want to talk about is the reservoir discharge status. And this model is, let me just turn some things on here. Okay, so this model here, and by the way, these will all be available in our library. They are available in our library, but I have kind of standardized all of the models that I'll be showing you. What I mean by that is they all have a kind of similar look and feel and size, and kind of a similar way that they're operating, such as instead of having a massive time series in here that has real data from a real gauge site, I just put in a stochastic element that you can replace if you put this into your model to play with, just for simplicity. It's a lot more work for me to maintain time series of historical measured flows, and it's just, it makes things more busy. So I've simplified things, but the basic logic is the same here. So, okay, so what this does is this model uses a status element that essentially will determine whether or not we need to make a change to our controls to make an outflow request on this reservoir. As we're walking through time, it will look at the current state of the reservoir, and it does that by monitoring its water level. So in this kind of model, in order to do that, then we need some sort of relationship between elevation and volume. So that can easily be done with a lookup table, which I have here. And then from that lookup table, we use the volume to calculate a water level. And so we're monitoring this water level over time. And what we want to do as uncontrolled inflows are entering the reservoir, we need to react to it. And I realize that in your models you might be working with, that you might not always have that scenario. Sometimes you have controlled inflows, sometimes you don't. And so I realize that's a bit of a simplification we're using here. But what we're doing is we're just saying, these are the inflows coming in, and we need to react to it. So inflows come in, we don't know what they are. They could be changing over time. And as that happens, this water level is going up and down. And when that does, then we need to react in order to try to maintain some sort of target zone or level within the reservoir. So what I have set up here is a target elevation, and that's just a constant. Now, that doesn't need to be a constant. We could have a target water level that is dynamic. That is often the case, especially when you need to account for a wetter period of the year, maybe for flood control. Then maybe you would have the target be dropping, going down lower in anticipation of higher flows, right? So you could imagine you might just replace this element with maybe a lookup table that is changing by the seasons or something. Anyway, this is constant. So we're trying to compare the current water level we're calculating to a target. And when we make that comparison, then we can make a decision at any point in time. Not at any point. We make a decision when the water level is when the relationship between those two is such that we want to make a decision, we can. So what I'm doing is I'm saying when the water level exceeds our target elevation, then we want to have an outflow. We want to turn on an outflow. So I call this discharge on with the status element. The status element is really important because it allows us to not immediately make a change every time we might cross that target boundary. And the reason I say that is because you have a big model, right? So this might be in a really large model, and you might have inserted time steps, many short time steps perhaps, and you don't need to be switching on and off repeatedly as your water level is bouncing around just little tiny bits around the target level in very small increments. Rather, we want to delay the decision and allow the water level to kind of move further away from the target before we make a change. So we can do that with a deadband. A deadband is nothing more than just a little bit of a zone that we add, and this is just a depth value. We just allow it to draw down a little more below the target before we turn it off. And you can do it on the off or the on side or both if you want, but let me show you what that does. So if I open up the status element and then we look at the triggers. So the way a status element is, it has a trigger for true and a trigger for false. What I mean is, if this element has a true status output, then we can turn it to a false. We can switch it to false by triggering the false trigger. That's this bottom one. And so we can trigger it back and forth between true and false. And in our case, true means on, false means off. Okay, so the true trigger, if we look at this, on true, and I just need to make sure that I'm still recording. Okay, the on true trigger, so this triggers when, so we have different types of triggers that we can specify, right? When the water elevation is greater than the target elevation, then we turn the discharge on. Now, the fact that this is on true is important because it could be different if we said at stock test. On true, what that means is it's going to wait until our next scheduled update in time. So I have 1 day time steps. And what this means is the water level is going to be greater than the target. That won't occur exactly at the change of a time step. Our time steps are changing at midnight every day, unless there's an unscheduled step. But the water level, if it increases over the target in the middle of the day, this will not trigger in the middle of the day. It waits until the next update, and that's when it gets evaluated. So just keep that in mind. When you do on true, it evaluates at the next time step change. So it's very likely, actually, probably all the time, your water level will be, even if you said greater than or equal to right here, it would be greater than the target because some time has already elapsed after this has become an actual true statement until it gets to the next time step. Okay, so what if you wanted GoldSim to just know exactly when it's going to hit this point and insert a time step? We could do that. We could tell GoldSim to insert a time step at exactly the moment that this condition becomes true and then make the switch. That's a kind of a rare thing that you'd want to do, but you could do it. And if you did that, you would want to change this type to at stock test. That would cause GoldSim to insert a time step and make the switch exactly at the moment in the day when that becomes true. So I wanted to make that clarification. Okay, on the off side, then this is where I incorporate the deadband. So now I say when the water level is now below the target and then minus a deadband, so minus this buffer, and this is a way to prevent rapid oscillations, then it will cause the water level to draw down below the target somewhat by this deadband amount before it makes the switch to turn it back off. So what we should expect is that when we run this model, we should expect that we're going to draw down below the water level, or sorry, below the target. And you can see that we do. So what happens here is at the very start of the simulation, we are slightly above. I'm going to make this a little bit bigger. We are slightly above the target at the beginning. So the pump or valve or whatever we have, the discharge is on, and the pink magenta line here represents the flow rate, and that is shown on the Y1 axis, flow rate. So we are discharging at a constant 100 cubic meters per day, and then it discharges, so you can see the water level is reducing well below the target before it makes the switch. And that's because our deadband is an entire meter, and the depth is shown over here on the Y2 axis. So that's on, and it shuts off. The water levels begins to build again, and then when it hits the target, it turns on. So that's how this thing works. If we inserted time steps, it should still pretty much operate this way. It'd be a slightly different, but for the most part, similar. If you had just an if statement instead of the status, if you just said if water level is greater than target, turn on, else turn off, that kind of logic is problematic, because if you had very short time steps, then you would have a much different response here than what we're showing. And so that means your model is dependent on the time step length, which we don't really want, right? We want it to operate the way it should be operated regardless of a time step length. And so this kind of logic would allow us to do it. Now, this is a simplistic approach because our discharge rate is constant regardless of the water level. And that is something that's not always hydraulically possible, right? So a lot of times you have maybe a weir or an orifice or something where water is flowing through it, and the flows are heavily dependent on the water level. And that if that's not the case, or for example, sometimes you have a model that it's not going to make a big difference in the long run. So you should evaluate that as you're building a model. Do I need to show a flow rate that's a little more realistic that incorporates hydraulics or not? And if you're just doing a simple accounting and you're saying, you know what, I just want to know basic average daily flow, it's okay if I don't have the Weir equation in here, is not always necessary. So this could be good enough, right? You could put in average daily flow and it would be good enough. But oftentimes you need a little bit more than this. And there are reasons for that. Sometimes you get in situations where you have a small volume relative to the outflow, and you have a very sensitive response in the water level to the flows. And in those kind of cases, you need something else. You need to have maybe a rating curve, which we can talk about now. So let's go to another model that shows that. Okay, so this model is it doesn't have a status element. Similar setup though. We're calculating a water level over time, and we have a target elevation. And now what we have instead of a status element is a rating table. This is quite common, but I want to talk about a few things with this. So what we do with a rating table is we're looking at the depth of water from the target. I think that's what we're doing. Yeah. So if we go to this lookup table, then what we have here is it's a relationship between a discharge rate and a depth. And it's, in our case, it's the depth above the target level. So when water level is above the target, then we will discharge at a certain rate. And as it rises higher and higher above that target, the flow should be changing according to this table. But the important thing is when it drops below the target, this table, we should be able to have a table that would then cut it off. And that means well, probably in this case, what might be better than saying to extrapolate would probably be do not extrapolate, depending on what I have in the table. And the reason for that is, let's look at the table. So what the table says is when we get to a zero height, that means water level is at, and because we're not extrapolating, the water level is at or below the target. That's will be at zero. The depth will be zero if we are at or below the target, right? And when that occurs, our discharge request will be zero. And anything above that would then increase, and we can have it increase very rapidly once it reaches a certain point or something like that to kind of mimic perhaps opening additional valves or maybe a spillway or something. And this is, again, this is a rough um, representation of perhaps a more complicated real facility, but quite effective and helping us to model something that is more complex than what we had previously. Okay, so let's look at the chart of this one. So this one is showing us how the water level in blue is below the target in green. And so our discharge, that's this magenta line here, the outflow is zero. And then once it crosses the boundary and goes above the target, then our flows begin to increase. And then you can see that the relationship between the depth over the target to the flow is not a linear, right? That's because we're using this table. And as the water level increases above about 0.5 meters, or I think it was 1 meter, once it's above 1 meter above the target, when the depth is greater than a meter, then the flows greatly increase right here. And so this is an effective way to simulate a more complicated outflow facility there. And then you can see it's dropped below, at, and below, so the flows are zero, and then back up again. So this this is useful, definitely something that could be used in many models. But I also wanted to make mention that we have two different elements here that are dealing with the discharge. One is a discharge request, and the other one is a discharge rate. And the reason I make the distinction here is because I feel it is important. This is my opinion, but I feel it is important to separate the flows from the information that we are passing around in our models. Not necessarily in this model because it's so simple, but in big models, it makes a really significant difference in the visual impact and helping people reading your model understand it when they can see the flows moving around. Now, what I mean by that is, let's say we have a big model here and I want to show just the flow network. I want to show just where the flows are going. So I might have a thing here called, water balance, or let's just say water balance. This is where I'm putting all my flow nodes, right? So I might put everything in there, but I'll organize it in a way that categorizes everything by component of the water balance. So I have an inflow, I have a reservoir, and I have a discharge. Those are the components of the flows. Everything else is just driving those flows, right? So I'm going to create another container called reservoir, and let's say it has a name, right? Reservoir 01, let's say. So that's the name of this reservoir, and now I'll put everything related to the reservoir in there. That's going to be this and this and this and this. So I'll put that in there, drag and drop that in there, and then update my expressions. Update my expressions then causes this influence line to be redrawn. If I go up here to model, you'll see there's update expressions. It's F9 key. Okay, so this model will be operating the same. If I run this, we get the same result. There it is. And you can see now we can see where the water's going. The water goes from here to here and then to here. And our request is still, something else. The reason I wanted to make this distinction is because oftentimes you're not doing things this way. You're not necessarily driving flows based on this reservoir. You might be driving flows based on a different reservoir somewhere else, right? And so you might be saying, well, there's this other pond over here, and when it starts to go dry, I need to turn this pump on that's way over in this other place, and then send the water over there or something like that, right? And so the best way to do that, in my opinion, is to calculate what the requests are, and then send that request over to the other place, and then have that drive the flow that goes to another place. If I did not have the distinction between the request and the outflow, then I would end up with something something totally different that would look like this. I would not have this thing right here, and I would have this discharge just being called, I guess, discharge. And then I guess that would go, I mean, if I moved this out here, the model would still work. Let's see. But I would end up with something like this, right? Now I have these two lines, and now we're all sitting here wondering, where's the water going, right? It looks like it's going two directions. And it kind of is, I suppose, but it's not. This arrow here is not water. This arrow, if I double click on it, is multiple things. It's information coming from the rating curve. It's information coming from the reservoir telling us what the water level is, and it's the target. So it's just an equation, right? It's just an equation. And so in a large model with many storage elements where water's moving around, it's really important to not be mixing these two things together. So I'm gonna put this back in here. I'm going to call this the discharge request. And then I'm going to into the pool element and making sure that this is looking at the discharge request. And the reason it didn't pick up on that change I just made right there is because I made a move. I moved it, and it didn't pick up the change yet. I should have hit F9 before I came into the pool element. But anyway, okay, so just be careful when you're moving elements. When you make a big move, moving elements from one container to another, update your expressions before you do anything else. Okay, so anyway, there's the discharge request, and now I have a pool element with a new outflow called pump discharge, right? Let's go back to that again. Go to the Outflows tab. The discharge request is being made here, and that creates this outflow called pump discharge. So that is now one of the outputs in our outflows called pump discharge. So that means now I can go to my other place wherever I'm sending this water, and then I can refer to that. So I'm going into the outflows of that reservoir. So separate from, I'll just say res 01 outflow, separate from the request, right? Okay. Anyway, so that's a rating curve. Let's go on to another one. Let's look at a recession curve. This one I haven't seen too much, but it's also an effective way to attenuate flows as the depth between, or the difference, I guess I should say, between some current water level and its target in a simplistic way. And so the recession constant, what I'm doing here is I'm saying how far above the target are we currently? And based on that, I then apply a recession constant to that value to calculate an outflow. And so the recession constant is going to be a rate over time, just a unitless rate over time, or in this case, percent over time. And what it means is, of the volume of water that's above our target, how much of that do we want to try to remove? And so we have this new thing called operating volume that I'm calling it. This is the calculated amount of volume of water above our target. And I do that using the same elevation volume table. and then I just calculate this as an operating volume, and that's the current reservoir volume minus the volume that would be at the target. So I'm doing another lookup on that elevation volume table at the target level, and I figure out what that volume would be. That's a static volume in this case. I separate the total volume from that, and then I do a max function of 0 so it doesn't go negative when we're below the target. And then I get that operating volume, and I multiply that by our recession constant. And so now when we run this is a much simpler method than the rating curve because it just requires one recession constant. So a very simplistic way to look at things. And this, as you can see, our discharge does increase rapidly as our volume increases above the target. But it is volume based, and it may or may not be sufficient in representing the spillway or flood controls that you might have on your facility, but definitely something worth looking into for simplicity. Okay, another one is, and these are getting a little bit more complicated. Let's look at a head loss calculation. So now we're looking at hydraulics, and what this is a I'm using the Bernoulli's energy equation to calculate head losses between the reservoir water surface and the tailwater at the downstream end of the where the outlet of the dam discharges into whatever downstream water body we're discharging to. So that would be like a downstream river or inlet box or something like that where water is discharging to. And so we take that water surface and we compare that to the water surface in the reservoir, and we know that there must be some sort of head losses that have occurred between those 2 points. So applying the energy equation, we can then figure out what the flow would be that would equate to that amount of head loss. And this requires iteration to solve for this. And so in here we have a script element. If I go in here, here's the script element. What we do is we use the Hayes and Williams formula for calculating friction losses. And we do that by, the first thing we do is we guess a flow rate. And with this guessed flow rate, we calculate all the head losses from that, including minor losses from pipe bends and valves and so forth. And we figure out how close we are to the actual difference in water levels. And then if we're above or below it, we repeat it by cutting the value in half. So it's a pretty fast and efficient way to solve for it. It's called binary search algorithm. And as soon as it converges, then it breaks out of this while loop. You can see right here, here's the friction loss, head loss equation. It's not really all that complicated, but essentially it just, once it converges, then it says, okay, our calculated head loss is pretty close enough to what the difference in water levels are. That's going to be our flow rate. So we calculate the flow that way. Now, one thing you want to keep in mind when you do this kind of calculation, typically, unless you have a sleeve valve or some sort of control valve that is breaking the head a lot between the upstream and the downstream side, we're going to be talking about pretty large flows here, high flows, or very small time steps. So previously I was showing you 1 day time steps. So if you have a 1 day time step, then in order for the hydraulics, the hydraulic calculations to be producing such high head losses. Well, and I say they're high head losses because I'm assuming that there's quite a big difference between the upstream water level and the downstream. I'm showing a tailwater level of 35 meters and an upstream of 40 meters. So a 5 meter difference is quite a bit of head loss. So that would be, we'd need a pretty high flow. So anyway, I had a choice with the numbers I was using in the other examples. I couldn't reproduce it unless I had a very small difference in tailwater and water surface, and that kind of didn't really seem to make a lot of sense to me to have such a small difference. So I changed this model to have much higher flows. So in this model, we are talking in terms now of cubic meters per second instead of cubic meters per day. And I'm also talking about uh, a much larger reservoir. With gigaliters instead of just a small amount of cubic meters. So anyway, much larger system. But as we run this model, let's see what happens here. Okay, so similar kind of thing here, except that you can see that the response is looks quite a bit different here. And that's because we have all of our discharges going through just this one pipe, right? So that's the response that we see based on the increasing water level above our tailwater. And in this case, by the way, our target level is the tailwater. So anytime the water level is above that green line, that's the tailwater, then we will have discharge out of this pipe. But anyway, in the cases in which you might want to incorporate hydraulics into a system, such as a long pipeline that is under pressure, discharging from below the dam out to an outlet works, into a submerged outlet, then this could be a good approach for you there. So anyway, similar, everything else is quite similar. We end up with a discharge request, which is the flow based on the hydraulics of that pipeline. That becomes our request, and then the ultimate rate is then calculated as the output of this reservoir. All right, so one other thing I wanted to show was a PID, which may not be it may not be as commonly used. This is more commonly used in something like regulating a water level in a tank. So what it is, it's a proportional integral derivative controller, and it's used to regulate flows that and prevent rapid oscillations in the controller. So if you're, for example, turning a pump, maybe you have a variable speed pump that you don't want it to be rapidly changing its flows, even if the water level is changing rapidly. Instead, what you want is it to more gracefully respond over the long term to changes in the water level. Then you could use this PID controller, and what it does is it calculates the difference between the water level and your target, and it calls that the error. And the error then, so that's the difference between target and water level. And then from that, we calculate three terms. We have the proportional output, which is going to be the error over time. And all of these terms, by the way, are multiplied by a rate constant. These rate constants are just a way to, I guess, prioritize each of these various outputs, because we sum them, and that is how we drive the discharge rate. The integral error is more of looking at over the long term, what is the long-term change or difference between the water level and the target. It's just integrating that error over time. This is a way to essentially say, if we have a water level that is staying consistently above the target over a long period of time, then this parameter becomes quite important. and it's going to try to move us away from doing that kind of a thing. It's going to penalize us heavily when we have a systematic over long period of time difference between the target and water level. And then we have the derivative error, which is it's the change from what the error was previously to what it is right now. And so that is a more of a rapid response type of output. So these three things, you can then weight them with these coefficients that are applied, and then we add them together and we come up with an outflow. So that's how the thing works. So when I run this model and we look at this response, I ran this over a longer duration because it's kind of better to see it over the long term. And you can see here over on the Y2 axis, that's the water level as it's varying from the target. So you can see here, it's rising below and above, it's going up and down. And the question is, well, why does it drop down more than before and actually rises above more? And this is because the integral term is being applied more heavily in order to, over the long term, get it to kind of be more equal above and below over a long period of time. And so this type of control logic is probably better for rapidly varying inflow rates with a smaller volume storage component. So like a tank, I would say, where this could be more applicable. And you can also tune the controller by adjusting those rate coefficients to get a better response. So these are some of the major ways of controlling. And now, obviously, there's a lot of other things you can do with the hydraulics, right? On the hydraulic side, so you might have a spillway or maybe a more complicated set of outlet structures that you want to model. But in addition to all of this, we also have the variability in the human interaction with the facility. And so that's the last thing I wanted to talk about. And unfortunately, I don't have a really great example at the moment. I do have more complicated examples, but I didn't want to get into those. But what we're doing here is I'm going back to the original example of our regular status example where we just turn something on and off and it's a constant rate. I'm adding in there a delayed response because what I wanted to do was say, well, what if it takes, a day or up to a day for or more for somebody to respond to this changing water level. I don't remember what the delay was I used. Okay, I used 1 day. I said, what if it takes an entire day for someone to respond and make a change to that pumping rate? So we could incorporate those kinds of things into a GoldSim model quite easily. What it requires, though, instead of putting my equation directly into the status element like I had before, where I said water level greater than target right here, I changed it. I said, I want to put that into an event because I want to delay that event. So I'm now referencing this delayed event. So I changed the type from on true to on event, and then I put it into this event that's sitting out here now. So the event, all it does is it says, okay, I'm just going to take any events that you give me and delay them. So now I come in here and I have a trigger on event and I've delayed it by 24 hours. And that on delay is the same function we were using before, water level greater than target. Same thing we were doing before. So when the water level is greater than the target, then what I want to do is I want to delay that by this delay time. You can see here that I'm using a scenario data element because I wanted to compare with and without the delay just to see if is it worth even looking at. So I have 2 scenarios, with and without delay, and then I run both of those. And then we can look at the result here. And what you see here is during the kind of this critical time of when we have this high inflow. And by the way, I think I changed the time step. Yeah, I had to change the time step because when you're dealing with these kinds of delays, um, a 1 day delay with a 1 day time step is kind of a kind of a coarse view of things, I would say. Instead, if we had maybe a 2 or 3 or 4 day delay, then maybe a 1 day time step's okay. But with my delay time being the same as the time step, it's a little bit coarse, and so I added more time steps. But anyway, you can see here there is an impact of water level due to our delay that we can see immediately. And you can see every time um, the difference here, the dashed line is with our delay turned on, and the solid line is with the delay turned. There's no delay. Um, and if I zoom in, then you can see here we had this high inflow coming in. It's the same for all the scenarios. And we also had a different starting point where I'm pointing at on day 37 because of the differences in our history up to that point. But we can set that aside for a second. When we rise above our target, if we react immediately, then we can draw that level down pretty quickly. But if we have this delay, then it rises up a bit more. In our case, only about less than a half of a meter, but still, depending on your system, could be quite significant depending on the scenario. So that's one way to incorporate delays in here. And if you were to go down this path further, then we would probably want to start looking at failure modes. If you were going to start looking at, the reliability of both the human interaction and the components, the mechanical components, and the facility itself, then you'd probably start wanting to look at reliability. And we do have a reliability module, and there have been other webinars I've given where I have incorporated that module to look at a bigger set of possible failure modes and delays and time when we're doing repairs, when parts are not available, things don't work right, things like that. It's definitely a lot more of a detailed analysis than what we've been talking about before. So that's something to consider. And also that some of these delays are um, could be somewhat short in duration compared to your time step. So something else also to consider. But anyway, that is everything I wanted to show you. So I'll go ahead and stop here, but I will wait around to see if there are any questions. I hope this was useful. I think that a lot of these discharge equations or methods that I was showing are quite useful for a lot of the very common models that are being built in GoldSim right now. I do see a lot of models coming from customers when they ask questions, and a lot of these types of methods I do see being used or maybe attempted to be used, and so I feel like it's important for you to see them. But thanks for joining us for this webinar, and we hope to see you next month.